All right, let's get started. So, any questions before I get started? Logistics, there was a question that I promised to answer, which was how to turn in the homeworks. And after much discussion back and forth with the GSI and the reader says that he will be better able to provide you with useful feedback if he gets paper. So the homework will be due at the beginning of class on Tuesday. Okay? And so if you print it out, that makes it more convenient for him to be able to give you more concrete feedback. All right, any questions? Comments? Yeah. Yeah, you should print the diagram and make sure that it is sufficiently self-explanatory what it does. So put in comments. Do you know how to put in comments in a LabVIEW diagram? Apparently all you have to do is click and start typing. Although it's apparently not obvious that that's what you do, but you can put comments in the diagram that way. So make sure that your diagram explains what you did. One of the goals of these kinds of block diagrams is actually to be readable descriptions of systems. If you find that you have trouble explaining it, don't hesitate to go ahead and send it by email to me or to one of the GSIs. Okay, it might be a useful supplement to the printout. Any other questions? Okay, so last time we were talking about state machine models, and I spent a good part of the lecture on characterizing the input and output of this garage counter. And just to remind you, what we settled on is that the inputs would be discrete events which would occur in time. So time is going to be modeled as the real numbers, and the input up is a function that maps the real numbers into either present or absent. And we call such a function a pure function, where the value can only be either present or absent. That's what we mean by the term pure. And the up function will be absent almost everywhere, but it will become present when a sensor detects the arrival of a car. And that's an instantaneous action. So it becomes present at an instant in time. It's absent immediately before that. It's absent immediately after that. So it's just a single discrete event that occurs at a singularity in time. That's the model. Now, how good a model that is of how a sensor behaves, well, kind of depends on how you design your sensor. It might not be a bad model. It's obviously not an exact model of any physical device because such singularities don't really occur in physics. Physics tends to deliver more continuous behavior. But that doesn't necessarily make it a bad model. You don't always want your model to be a precise description of the physics. You want it to be a representative of the behavior, and then you want your physical implementation to have, to be able to match that behavior. Does that make sense? Okay, so the counter, in this case, we're assuming that it has a finite number of states, so it's going to count, it's configured for a garage with m parking spaces, and it's not going to count beyond m. And so we can represent that using a finite state machine diagram, bubble and arc diagram, where we use a bubble for each state. So the initial state, which is represented by this little dangling arrow right here, is 0, meaning simply that when we start this thing up, we assume there's no cars in the garage. By the way, that would be a problem because presumably this system would need to get restarted upon occasion when it fails. And if it always starts in state 0, then it's not going to be very accurate because odds are there are going to be cars in the garage. Okay, but these are the kinds of things that you can work through fairly concretely in a design that is represented explicitly this way as a model. Whereas, for example, if I just gave you a textual description of what the requirements of this thing were, I might leave out altogether what the initial state of the system is when it boots up. I might not say that in the document, and consequently I have a very incomplete specification. Here I am actually saying what the initial state is, and I've made a rather poor choice in practice, right? So, but at least I'm being explicit about what the design is. So the transitions are annotated with the key thing to look for is this little slash. So everything that comes before the slash is a guard, which is a predicate. Predicate is an expression that evaluates to true or false. In the case of pure inputs, we will assume that the expression up will be true at times where the input up is present. So if the state machine reacts at a time when the input up is present, then the value of this variable up will be true. So this expression means that up is true and down is false. And we interpret down being false to mean that at the time of this reaction, that the down input is absent. Now, I should point out that this notation has flaws, right? So what if in my guard I want to do division? Well, I might use a slash to do division, and then you kind of we have an ambiguous syntax, right? Does the slash mean division, or does it mean the separator between the guard and the action? In this case, it doesn't mean division. What this means is that this is a guard to the left of the slash, and to the right of the slash is an action, and it's specifically asserting a value on the output. Okay? Now, the output value will have value 1 at the instant that this reaction is taken. So this reaction occurs instantaneously at a time when the up input is present and the down input is absent. That's when that transition will be taken. At that instant in time, the output will have value 1. What will the value be of the output immediately before that? Will it be 0? This is actually a key question about our model. Well, it kind of depends on how we do our model. Okay? In the models that we use in the text, the outputs occur only when the transition is taken, and when you're not taking a transition, we assume that the output is absent, not 0, right? Now in fact, if you've seen state machines before, you might have seen a different flavor of state machines where the value of the output is associated with a state rather than with a transition. Okay, you could do that. You could say, well, when I'm in this state 0, then the output is 0. When I'm in the state 1, the output is 1. And the nature of the output signal will be quite different in that case, right? So let me attempt this technology again. Okay, if the output is a signal C for count, it's giving us the count of the machine. It's going to be a function that maps the real numbers into something. Okay, the question is what? And in the state machine model that I've given you, we're specifically assuming that it maps into either absent, okay, or a natural number. Can you see that? No. Sorry. There we go. And we're going to assume that the output is in fact discrete and that it's non-absent only when a transition is taken. Okay? We could have constructed a very different state machine model that would have a function C prime that maps the real numbers into the natural numbers and is never absent. And while it's in state 0, the output is 0. While it's in state 1, the output is 1. While it's in state 2, the output is 2. Okay? That would be a different model. All right? But this is the model that we're using by default. And the reason that we're using this model is because we're using state machines primarily to model discrete actions. And discrete actions we're going to model as sequences of instantaneous behaviors, not as values that are held over time. That might be a good description of a circuit implementation, But it wouldn't, for example, be a good description necessarily of a software implementation, which is more about discrete actions. Okay. So it's a choice, but it's a modeling choice, and it's a choice we make. Okay, so that's what we mean by this state machine model. Yeah. Question.
I guess I'm just curious. The number of cars in the place is constant over time, right?
Yeah. Right. So you're sort of saying that, well, gee, maybe this second alternative is kind of a more natural description of the system, because at any given time it tells me how many cars are in the system. Well, I mean, you're right, but it's a choice. You make a modeling choice, right? And the point is that you want to be explicit about what your model means. Okay? And yeah, question. Okay, so this is, the notation here is that a function always, you give wait a minute. I think if I go to full screen, maybe it'll become visible. There we go. A function is always part of a function definition is two sets, the domain and the range. And here I've given the range, okay, is a union of two sets. The natural numbers and a set that only has a single element that we call absent, which is not a natural number, right? And what we mean by this is that the value of this function at some real number r, so c at some real number r, will either be absent or a natural number. That's what that notation means. Okay? Was that your question? Was getting at the notation, or? Oh, it's just a symbol. It just means there's nothing there. Okay? The absent represents the fact that I'm not producing an output at that time. Right. So the state machine model that we're using here produces outputs only when a transition is taken. Otherwise, it does not produce outputs. Okay? And so not producing output is represented as the value of the output is absent. Yeah, question?
The empty graph would be the zero or the absent.
I'm sorry? Say it again.
Would be the zero or absent state, or absent output would be.
Yes.
I'm saying that you still have natural or natural numbers, so there is still zero. So
Yes, that's true. But notice there's potentially another flaw in this design, right? When is the output 0 produced? It's only produced when the last car leaves. So when you initialize this system, you do not, in fact, produce the output 0. So if you're using this to drive a display, right, the display will not show 0 when you boot this thing up. Okay, potentially another defect in the design. You might want the display to show 0. Yeah.
and also, would you be able to set, like, you won't be able to move all the cars?
That's right. So, yeah. So I mean, this design kind of assumes that if you have to reboot the system, you also have to evacuate the parking lot and get all the cars out of it. Pretty flawed design. Right? But if I had just given you a description of this design in English text, we wouldn't have seen all those flaws. Right? That's the value in the modeling, is that you can kind of look at what the details of the design are. What are the behaviors under different circumstances? By the way, these kinds of models can be very systematically explored. So you can define states in a state machine that are, for example, known to be unsafe. Right? There's more than 45 cars on the third level of the parking lot, which is not designed to hold that much weight. Okay? Something like that could be represented as a state machine. And if you have some way of controlling the cars, you could do a systematic exploration of the design and prove that that state can never be reached. That's a proof of a safety condition. An extremely valuable thing to do when you have safety critical systems. Okay, is to be able to prove safety conditions on your design. Being able to do systematic exploration of the behaviors is the whole reason we construct these very precise models. Now, okay, so that's the guard, initial state, output valuation. Notice that here in the transition, when I give a transition from one state to another, I give a guard and an output valuation. If my state machine has only a single output, like this one does, it only produces this output count, then I don't really need to name that output. But you could have a state machine that produces more than one output. So it might produce an output count and an output, how much money it's collected. Okay? In which case you need to modify this and you need to say which output is taking which value. So count is getting some value, say 1, and money is getting 2. If it costs you $2 to park there or something like that, right? So you can augment this by being explicit about which output you're talking about. All right. But if there's only one output, then we don't bother naming it on the transition. Okay. So associated with this diagram is a formal model. And by the way, does anybody know what the term formal means? Does it mean you're wearing a tux? Yeah. Yeah, it's governed by mathematical rigor, but it has actually a really deep root, right? I mean, it's actually the same root as the word form, right? And what formal actually means is it's devoid of meaning. It has only form, no meaning. Okay? That's actually right. So, yeah, so a formal model, okay, is a set of expressions that you can manipulate without having the slightest idea what they mean. Okay? You have a set of expressions and a set of rules for transforming them, and these rules enable manipulation of these expressions such that you start with valid expressions, you end with valid expressions as you apply these rules without having the slightest idea what the meaning is. That's actually an extremely valuable property because if we step back and we give these things meaning, then we can, because we carefully design the rules, we can ensure that the transformations preserve truth even when we don't understand the model. So if you start with something that's true, you do a sequence of manipulations, you end with something that's true, even if you don't understand the model. That's the key point, right? So formal enables you to do manipulations of things you don't understand, which is extremely valuable because that, for example, enables exploration of behaviors before you completely understand your model. So this diagram falls a little bit short of being a formal model because there's ambiguities in here, like does the slash represent division or does it separate the guard from the output, things like that. But we can reduce it to sets and functions which do have formal properties. There's a logical system that is mostly self-consistent, not entirely it turns out, but mostly self-consistent. And it has the property that if you start with things that are true and you perform these manipulations, you end up with something that's still true. So, a formal model that's equivalent to this diagram asserts that you have a set of states, in this case 0 to m. You have a set of input valuations. The input valuation, this set of input valuations is actually a set of functions. It's a set of functions that for each input to your state machine, give it a value in a set. Okay? You have a set of output valuations, and then you have an update function. And the update function, given a current state and an input valuation, will yield a new state and an output valuation. Okay? So this diagram is actually a description of this update function. It's a somewhat informal description of the update function. It can be much more compact than, say, you could describe the update function as a table. For these inputs, you will produce these outputs and move to this state. But that table can get very big very fast. The diagram may be a much more compact and readable description of that function, which is the reason we use it. Does that make sense? Okay. So the state machine notation looks like that we're going to be using. The guards are predicates. They look like this. This is for pure signals. So if we have a guard that is true, that means that transition is always enabled. If we have a state machine model similar to what I just showed you that happens to have a transition like this, how long do we spend in this state? Yeah, so it turns out that is not an easy question to answer without having a little more context, right? Because we need to decide when this state machine is going to react. Whenever it reacts, we will take that transition. Okay? But one thing that the state machine model by itself doesn't say is when does the state machine react? Yeah.
Couldn't you almost use this state machine notation as a way to characterize the timing?
You can, in fact, and in fact, we're going to do that. I'll show you how to augment these state machines with continuous dynamics, and we can build what are called timed automata, which are in fact very compact descriptions of fairly complicated timing behaviors. Okay, so we're going to do that. But for now, keep in mind that the guards get evaluated only when we choose to have the state machine react. So for our garage counter, when do you think we should have it react? Well, let's look at the block diagram for this garage counter. What would be a reasonable choice? When should that counter block react? Yeah, when one of the inputs is not absent. So that would be an event-triggered reaction. Would it be okay to choose to have it react once per second? Yeah. Depends how fast cars are arriving. Yeah. Let's assume that our model is that the car arrivals are sporadic in precisely the way that I defined last time, which means that up is a function that maps the reals into present or absent. Almost everywhere it's absent. At arbitrary points in time, it becomes present, but there's a minimum amount of time between the times at which it can be present. That's what we mean by sporadic. So let's assume that's the case. So would it be okay then to have the counter react once per second? Yeah. Yeah. In fact, if you had the counter react once per second, you would almost certainly miss every single car arrival, right? Because at the time you react, the inputs would be absent with probability 1. Therefore, that counter would be useless, right? So it matters. We're kind of building the semantics of this model, what the model means as we go, right? But one of the things we do have to say about a model is when do the components in the model actually react to inputs? Now, because of this state machine design, would it be okay to say, well, the counter just reacts continually. It's always reacting. At all times, guards are being evaluated. Yeah. Yeah, so that could be a poor model from a fidelity perspective. You're pointing out it could be a dangerous assumption that is continually reacting because that would be hard to implement if you're implementing it in software. And that's true. But would it be at least a correct model? Would it count cars? Yeah, it would count cars. Because these transitions have guards that will only become true when an input is present, it would be okay, actually, to have this thing being continually reacting, because it'll just sit there in state 0, continually reacting until this condition is satisfied on the inputs, and then it would take the transition. Okay. These are really subtle distinctions between models that, by the way, when people do modeling out there in the real world, they usually don't even think about this. They sit down with a piece of software, and they try to figure out how the software model works. It's usually not very well documented. Right? You'll find this when you try to use LabVIEW state charts, for example, that much of figuring out what these models mean is about trying things and seeing what they do rather than reading documentation, because it's actually not written down very well. That's common, unfortunately. People don't think about these things when they build modeling environments. It doesn't occur to them that there are many different ways to do it. They think the only way to do it is the first thing they thought of. And so that's what you see often in reality. Okay, but in this course, we are going to think rather explicitly about what the models mean. So we can have signals that have numerical values, in which case we could have guards like this. We could say, if we just refer to an input by name, even if it has potentially a numerical value, what we mean by this is simply that that guard will be enabled if the input is not absent. Okay? Does that make sense? Whatever its value is. We don't care what its value is. It just has to not be absent. But we could also have this enabled if it is not absent and its value is 1, for example. That would be another guard. Or we could have it be present. We could have a guard like this. P equals 1 and P3 equals 1 and P1, which means that this third guard will be enabled if the input P3 is not absent and has value 1, and the input P1 is not absent, right? By the way, this is another potential ambiguity that can occur in the guards, right? What if I could have parsed this differently? I could have interpreted this as, well, this will be enabled if P3 is equal to 1 and P1. But 1 and P1 is not a well-formed expression, because 1 is not a predicate. So that parsing would be incorrect, but the notation is a little bit informal, and you have to be careful with that. Okay. Here's an example of a thermostat. So here, what we do with state machines is that we're explicit about what the inputs and outputs are. So we do that with this little annotation on a state machine. So this is a state machine that has an input named temperature, whose value is a real. Notice that in this case, I haven't explicitly mentioned absent. But in our state machines, the input that's always a possibility for it to be absent. So we don't have to explicitly mention it. Okay? So when it's not absent, it can take on any real value. The output is going to be two pure signals, one of which will turn the heat on, the other one of which will turn the heat off. If we will start in the cooling state, and when the temperature is less than or equal to 18 degrees, suppose that's centigrade or Fahrenheit? Hopefully centigrade. When the temperature is less than or equal to 18 degrees centigrade, we will produce the pure output heat on at that instant. At the instant of that reaction, the output will be present. The heat on output will be present. And what about the heat off output? Will it be present or absent at the instant that this reaction is taken? Absent. But again, there's an informality in the notation. I wasn't explicit about that. I didn't mention heat off. So we just assume it's absent if I didn't mention it. Okay? So then we switch into the heating state, and when the temperature is greater than or equal to 22, we will take this transition back to cooling and produce heat off output. Okay, does that make sense? Notice this is not a very robust design, right? Because if the heater is not working, right, and the temperature never gets above 22, there's nothing here that will detect that. So we probably would like to augment this with any serious thermostat, certainly in any safety critical scenario, with fault detection logic, right? So for example, it would do something like, if we are in the heating state for more than a certain amount of time and the temperature hasn't risen to 22, sound an alarm or something like that. Okay? Just a little bit more about this bubble and arc notation. We also have, we'll occasionally use, in order to make these diagrams more compact, we'll use these dotted transitions and or a transition that has a simple slash. Okay, the simple slash means the guard is true, it's always enabled, and the output is absent. Okay, and the dotted transition means if no other transition is enabled out of this state, then this transition is enabled. Okay, so by default, every state has one of these transitions. If no outgoing transition is enabled, we stay in that same state and we produce no output. Okay. Another notational convenience is, suppose that the number of spaces in the garage is big, 300 spaces, say. Then drawing this bubble and arc diagram could be kind of painful, and it would be pretty stupid, really, right? Waste of time. So we use what are called extended state machines, which have, in addition to the states that are represented by these bubbles, they also have states that are represented by variables. Okay? So in this case, I've declared a variable C. It has a data type that is given by this set, 0 to m. It can take on values 0 to m. This state machine has inputs up, down, which are pure. It has output count, which is a member of this set. And the state machine is given as follows. There's an initial transition that initializes the variable to 0. And then when up is present and down is absent and the count is less than m, then this transition is enabled. The output produced is count plus m plus 1, and an update action is taken, which is that we update the variable C by increasing its value by 1. Okay? And similarly, here, if there's a down event and not an up event, and the count is greater than 0, then we will produce as output C minus 1 and update the variable C to equal C minus 1. So for this state machine, how many states does it have? Sorry? M plus 1. Right? Even though there's only one bubble, it has m plus 1 states. Suppose there were 2 bubbles. How many states would it have with this same variable? Well, suppose, here, let's draw one. So suppose I have a state, I have a variable count whose data type is 0 to m, and I have a state machine with 2 states. Here's my initial state, and transitions. And these transitions have guard, output actions, and update actions. So it looks something like that. Okay, whatever the guards are predicates, the outputs are values in the output data type, the update actions are assignments to the count variable. How many states does that state machine have? 2m plus 2. Why? Because the value of this variable is part of the state of the system. And in addition, which of these two bubbles you're in is part of the state of the system. So in each bubble, you could have m plus 1 possible values of the variable. So overall, there's 2m plus 2 possible states for this system. Now, I want to emphasize that depending on what these guards are, not all of those states may be reachable. Okay, suppose, for example, that G1, the guard G1 is false, always. Okay? Then even though the state machine description has 2m plus 2 states, there's only m plus 1 reachable states. Sorry? There might not even be that many. In fact, actually, in this case, no, there is actually only one reachable state. Right, there's no updates that can occur to the variable c, so there's actually only going to be one reachable state in that system if the guard is false. Okay? So one of the things about this kind of notation, by the way, is that the size of the state space can get enormous very quickly. Systematic exploration of that state space becomes very important. So we're going to look at algorithmic techniques that will actually explore state spaces because you can't really do it by hand. The numbers get too big too quickly. All right. Here's a traffic light controller that has a pretty large state space. It has a count variable that can take on values between 0 and 60, and it's got 4 bubbles. So, quick pop quiz. How many states does this system have? Four times 61 plus 4, right? Now, we don't know whether they're all reachable until we do more analysis of the guards. But at least from the explicit declaration there, that's how many possible states this thing could be in. Okay? So the way that this traffic light controller works, so this is a good test of whether we're on the same page with the notation. Right? If you can just read the notation, what happens? Well, we start in the red state with count equal to 0. If the count is greater than or equal to 60, then we'll make this transition. Yeah, question?
Right now you said like 4 times 61.
Right.
You said like 2 times m plus 2.
Oh, you're right. It's 4 times 61. Yeah,
So that's
right.
plus 1.
That's m plus 1, right. Sorry, good point. Yeah, it has 4 times 61 possible states. Okay, so again, just to make sure, the point here is to make sure we can read the notation, because this is now a less trivial state machine. So we start in the red state with the count variable initialized to 0. If the count is greater than or equal to 60, we take this transition. Otherwise, we're going to take this transition and increment the count. When would it be reasonable for this machine to react? Should this machine react continually? It might not be a very good choice, right? Because how long will it take for the count to reach 60 if this is reacting continually? Well, be instantaneous, right? So there's not a lot of point in having this counter. I mean, the point of having this counter is we'd like the light to remain red for 60 seconds, say. In which case, we've got an implicit assumption about the context. This machine is going to react once per second. Okay? So once per second, it'll increment the count. Then when the count reaches 60, it'll take this transition and issue an output sig g, which will presumably turn on the green light. We will then remain in the green light state for 60 seconds unless a pedestrian arrives. No, I'm sorry. It's the other way around. We will remain in the green state possibly forever. Okay? The only conditions under which we leave the green state is if a pedestrian arrives. So this is at a crosswalk, presumably. This is controlling a light at a crosswalk, And it's just going to stay green unless someone pushes the button to request a cross. If someone pushes the button, at that point, if the green light has been, if the light has been green for fewer than 60 seconds, then we don't immediately transition to yellow. But if it's been green for more than 60 seconds, then we do transition to yellow. Okay? So the goal of this design is to make sure that the light doesn't turn green and then immediately go to yellow again. If it turns green, it's going to stay green for at least 60 seconds and let a reasonable number of cars through. Okay? That describing precisely that design in words is hard. Okay? Try it. Try to write down precisely in words how this traffic light behaves, and it's easy to get it wrong, right? Whereas this description is actually precise. Okay, is this clear to everybody? Can you read the diagram? Okay, then we agree on the notation. Just some definitions of terminology. You'll see a stuttering transition is an implicit default transition that is enabled when inputs are absent and produces absent outputs. So in particular, this, I can be in this green state, and if the count has reached 60 already, and the pedestrian input is absent, then what happens in the reaction? Well, neither of these transitions is enabled, and neither is the default transition because it's guarded by the count being less than 60. So none of the transitions are enabled. So I stutter. And stuttering means that the outputs are absent and no variables get updated. That's distinct from this default transition, which occurs if the count is less than 60 and does change the state of the system by updating the count variable. That's not a stuttering transition because it changed the state. Okay? So yeah, question. I'm sorry? Well, so this dotted line is really just, think of it as a lower priority transition. It's just like the other transitions, except that it only becomes enabled if all of the other transitions are not enabled. And some state machine notations actually give you an arbitrary number of priorities. You don't have just two necessarily, a high and a low priority. In fact, I think the LabVIEW state charts has that property. You can have any number of prioritized transitions with priorities relative to one another. And the issue is that the highest priority the guard on the highest priority transition is what you evaluate first. If it's true, you take it. If it's not true, you look for the next highest priority transition. And if its guard is true, you take that. Now, you don't actually need priorities, right? I could write this as an ordinary transition and augment this guard with the pedestrian being absent. But the problem is the notation gets sort of more complex. So the dotted line is just a shorthand for that, augmented guard. Does that make sense? Yeah, question.
Sorry, do we tend to explicitly avoid stuttering transitions, or are they okay?
Stuttering transitions are fine. They're part of the behavior of the system. And in fact, often there are defects in designs where you failed to take into account what happens when the thing stutters. Yeah. Okay. Receptiveness means that for any input value, some transition is enabled. This includes the implicit default transitions. So in fact, in our notation, all of our state machines are receptive. No matter what the inputs are, some transition is enabled because by default we can stutter, which is a transition. Okay? But you could come up with state machine notations where that's not the case, where only certain inputs are accepted. Okay? Determinism means that in every state, for all input values, exactly one transition is enabled. No more than one is enabled. But non-determinate transitions are sometimes useful. So for example, if I wanted to model the arrival of pedestrians at this crosswalk, one way to do it would be with a non-deterministic state machine. And the way this works is we start in the crossing state. If we get a green light, we switch to the none state, right? So that means the green light is on, cars are going through, right? So pedestrians are presumably not in the intersection. And none means there's no pedestrians waiting. And then one of two things could happen. Either we continue to have no pedestrians waiting, or a pedestrian arrives. These two red transitions are both enabled because the guards are true. So it's a non-deterministic choice. This specifies that either transition could be taken. In a reaction, either a pedestrian arrives or a pedestrian does not arrive. If a pedestrian does arrive, we're going to represent that by choosing this transition and switching to the waiting state. And then we go to the crossing state when the light has turned red. At that point, we assume all the pedestrians cross. And then when the light turns green again, we assume there's no pedestrians waiting and wait until some other pedestrian comes along. Is this a good design for a crosswalk? What happens with this design if a pedestrian arrives while the light is yellow and pushes the button and waits? Sorry? He'll stay there forever until he realizes that he needs to push the button again. Right? So this might not be the best design. Okay? How would we determine that? How would we find that design flaw? We would take this state machine, compose it with the traffic light state machine, and we would declare a safety condition. A safety condition might be something like, if a pedestrian pushes the button, this would be a liveness condition. If a pedestrian pushes the button, the light will eventually turn red. Okay? That's a condition that we could explicitly give as a mathematical formula. And then we could show that this composition of state machines does not satisfy that condition. And moreover, we can algorithmically find the counterexample that shows what are the steps that led to that pedestrian pushing the button and the light not turning red. Yeah.
Can you explain the non-determinism one more time?
Okay, so the guard being true means that this transition is enabled. So when I'm in this state, this self-loop transition is always enabled. So when this thing reacts, it's always valid for it to just take that self-loop transition and produce no output. But in addition, the transition to the waiting state is also enabled. Its guard is true. So when I'm in this state and I react, two of my outgoing transitions have guards that evaluate to true. We interpret that to mean that either transition can be taken. The model doesn't specify. It doesn't constrain the behavior. Both are legitimate behaviors. Okay, that's what we mean. And we refer to this as a non-deterministic state machine. Yes, question?
So does that mean when you're in non-state, with no condition attached, it just stays yellow? Is that what's the question?
Well, so I think what you're asking is how would we fix the design defect that we identified, right? Which is that if a pedestrian arrives while the light is yellow and pushes the button, this composition of state machines will not detect the arrival of that pedestrian and will not turn the light red. I'll leave it up to you as an exercise to figure out how to fix it. Okay, it's actually a good exercise. Yeah, question.
Is this like state machine generating pedestrians? Like we have to choose
Right.
we generate one. Is that like how the pedestrian?
Yes. So this is let's just let's be a little more explicit here. So the traffic light controller has as an input a pure signal pedestrian, right? This machine has as an output a pure signal called pedestrian. Okay, we can view this as follows. We have, our system is a composition of two subsystems, the pedestrian state machine, okay, and the traffic light state machine. This has a pedestrian input, this has a pedestrian output, this is a pure signal. Okay? When we form this composition, we have to say something about how these state machines react. Okay? I have implicitly assumed that these things are going to react simultaneously once per second. Right? It turns out now that I've made that assertion, I've declared how these things are connected, I've said how they react together, I can now translate this system into a single state machine, okay, where the state is a composition of the states of the two individual state machines, and now I can do a systematic exploration of the reachable states of that system. But I'm getting way ahead of myself here. These are the kinds of techniques we're going to be applying much later in the course to do things like systematically explore whether a design is correct and safe. Yeah, was there a question back there? Even if there's no pedestrians? So this traffic light, if no pedestrians arrive, will remain green. When? Oh, in the non-deterministic state machine. Yeah, this could actually, one of the allowed behaviors of this is that no pedestrians arrive, right? Because you could just be always taking this self-loop transition. That's a legitimate behavior of this state machine. Well, this is a model of the arrival of pedestrians, right? So it doesn't, let's see, how do I say this? There's nothing, okay, this is a formal model. It's actually devoid of meaning. Pedestrian is a symbol, not a human arriving and pushing a button. The human arriving, pushing a button is our interpretation of this model. Okay, but the model itself is formal. It just says that I have a component in my model, this one, right here, that at an arbitrary time could produce a pure output. And I'm going to interpret that to mean that a pedestrian arrived. Okay. By the way, this model actually has a feedback loop too. Like that, right? Because if you notice the model of the pedestrians react to whether the light is green, yellow, or red, and those inputs to this state machine are outputs of the previous one. Okay? So there's a feedback system here that you have to take into account when you look at the behavior. All right. When we're looking at non-deterministic state machines, we can represent behaviors as trees of possible behaviors. The difference is, well, actually any state machine, we can represent the behavior as a tree, but in a non-deterministic state machine, in a deterministic state machine, given a sequence of inputs, there's always exactly one path you take through that. In a non-deterministic state machine, there could be many paths you take through it for the same input sequence. Okay, so there's lots of uses for non-determinism. We'll see a few of them, and I'm going to now switch topics a bit. Why don't we take a 2-minute break while I switch topics, because it's gotten warm. People probably benefit from standing up and getting the blood flowing a little bit. Yeah. Yes.
I want to talk to you about my role as fast in the class.
Okay.
Might be a long one, sorry, just like I guess it's mostly, I'm probably thinking about any good classes after each class just because, like,
Started again. Achtung. Let's get started again. So this next part is less formal and in some ways a little more fun. But it also, what I'm going to be talking about now is in chapter X of the book, which means we haven't written the chapter yet. Eventually we'll write this chapter, but we haven't gotten around to it yet. But this is about sensors and actuators, which are a pretty important part of understanding cyber-physical systems. So there's a lot of different kinds of sensors you can use. Sensors are basically just an interface between the semantic world of software and the physical world. And sensors give you measurements of the physical world. Actuators cause you to have an effect on the physical world. And there's an enormous variety of sensors and actuators that we can talk about using: cameras, accelerometers, rate gyros, strain gauges. So I'm going to talk about a few of them, but first I want to show you a little video from a project called the PATH project. This is a Berkeley project. It's been funded for some time by the California Department of Transportation. Let's see if we can get a better picture. I apologize. This will not render well in the screen capture because apparently it doesn't do videos. But here, there we go. Okay, so what's happening here is this is a snowblower running near Kingvale, which is a town that you pass if you go up skiing in North Lake Tahoe. Okay, and this snowblower has no has hands-free operation. Okay, so as you saw there a second ago in the video, the driver could take his hands off the steering wheel, and the goal of this is to be able to have snowblowers operating in complete whiteout conditions where it's very difficult to tell where the edge of the road is, and have them be able to operate on a windy mountainous road and not, run off the end of the road. Okay? So my question to you is, what are the sensors that are being used here? Yeah.
Maybe a holodeck sensor into finding the guardrails.
Okay, so one possibility would be to something that would sense the guardrail somehow. How would it sense the guardrail?
You could use like a holodeck sensor.
Use a Hall effect sensor, so you could generate a magnetic field. You'd assume that the guardrail was some ferrous material, and you would measure your distance to that guardrail. That's a possibility. What if the guardrail has gotten bent? Cars run into guardrails, actually. So that could be a problem, but might work as long as you kept the guardrails well maintained. Yeah, other ideas?
Probably some sort of GPS, like precise GPS.
Yeah, so GPS would be another possibility. You presumably, as long as you could get the precision close enough, the precision would have to be very high. This thing is operating just inches from the guardrail, so you would need probably differential GPS, which uses a local beacon as well, which could be kind of an expensive solution, but it's feasible. Yeah, other ideas?
You could use something like
Laser
laser range scanners.
range scanners? Yeah. I think a challenge that laser range scanners would have, though, is that they wouldn't be able to see through snow. Right? So, in fact, they're optical, so in whiteout conditions, they would get completely confused. So that probably actually wouldn't work very well, I wouldn't think. Other ideas? Yeah.
I know some ideas were to put like coils in the ground, like the edge of the road.
Yeah. So you could put coils in the ground, and you'd have to power them if they're coils. That would be expensive. But then, presumably, if you have these coils in the ground, you could make them generate a magnetic field that you could detect using, again, a Hall effect sensor, which measures magnetic fields. But if you want to generate a magnetic field, do you really need power? Just use a magnet. That's what they did here. They drilled a hole in the ground in the road every 12 feet or so, and put a magnet in, and it was a precise distance to the edge of the road, and they used that to measure the position. Why would you choose every 12 feet? I mean, shouldn't you maybe choose? Shouldn't it be a continual stream of magnets? I mean, what's to keep the snowblower from suddenly turning? Yeah.
Probably want it just wide enough so you can pick up the next magnet before you.
Yeah, so that would be one possibility, is put them close enough together so that you can continually sense the magnets. But do you really need to do that? So there's a role that modeling could play, right? What are you driving on? You're driving on a road, right? It's a mountain road. What do mountain roads do? Do mountain roads do that? Not usually, right? They usually do more like that, right? If you do have a mountain road that does this, then presumably you would have to put sensors rather close together there, okay? But here, you could put sensors like that. Now, why does that work? Well, you can think of these sensors as samples of the road location. And as with any sampling schema, there's the risk of aliasing, right? Aliasing means that the snowblower could decide to do a path like that, right? But that would be stupid, right? So you design the snowblower so that it chooses a lower frequency of bends in the road rather than a higher frequency of bends in the road, and then you don't have to put the magnets quite so close together. And you use your knowledge about the structure of the roads to determine how far apart you need to put the sensors. Yes, question or comment? Did you have a question or comment? No.
Do you know how many of the magnets it can sense at once?
There's a video here that kind of gives a picture of it, and it pretty much only senses it when it's right on top of it. It has a bar across the bottom. Okay, it's a sensor array bar, so there's a row of sensors. All right, what it does is, one of the sensors will pick up the magnet more strongly than the other sensors. If it's a sensor to the left that's picking it up, then the snowblower corrects by driving to the right. If it's a sensor to the right, then the snowblower corrects by driving to the left. Pretty much exactly the same kind of feedback system as we saw for the helicopter control system. Okay. So, yeah, they have a switch to convert it to automatic, back and forth from automatic to manual. So this is how a Hall effect magnetometer works. It's based on the idea that if you have a metal plate like this in a magnetic field, when you pass a current through it, the path of the current is bent by the magnetic field. And so you can sense a voltage across the top and bottom here as a consequence of the bending of that current through that plate. Okay? So that's the basic idea of the physics. Accelerometers. We're going to use accelerometers in the lab. The sort of first challenge problem that you're working towards in the lab is having a robot climb a hill. And in order to climb a hill, it needs to figure out which direction to point in to head uphill, because it's not going to effectively climb the hill if you don't head uphill. So you can use an accelerometer to measure tilt, right? So what is an accelerometer? Well, it can be used, here's a sort of a cartoon of an accelerometer. If you put a mass on a spring, as you rotate this around, okay, you can see that in reaction to the force of gravity, the length of the spring will change. Okay? It's called an accelerometer because if I take that same bar and hold it like this and I just move it back and forth, then the length of the spring changes also. So it can measure acceleration, but it's actually much better at measuring tilt than it is at measuring acceleration. Okay? Because of this effect, it measures the force of gravity. If it's pointed straight up, the spring compresses. If it's pointed straight across, the spring is neutral. Okay? Does that make sense? These are the equations that describe that behavior. I think we can skip over those. But the fact that it can measure tilt is, given by that expression. But I think it's sufficient to understand the intuition here. Well, one of the difficulties in using accelerometers is that it's difficult to tell the difference between tilt and acceleration. So how do you suppose an iPhone does it? Right? The fact is, you all know probably that, the iPhone has this property that if I'm reading my email this way, it knows that I'm reading it that way, and if I turn it vertically, it switches. It switches. Damn. Come on, don't do that to me. There we go. So it's measuring tilt there, right? Okay. Now, imagine this spring inside, right? So what happens, say the spring is oriented vertically, lengthwise in the iPhone, right? So it's in a neutral position now. If I turn it this way, the spring gets compressed, okay? If I turn it back this way, the spring's in a neutral position. If I shake it back and forth like that, what happens to the spring? Well, it also gets compressed, but it's not rotating. Why?
Probably has some limit, has to be compressed for so long to the actual tilt.
Accelerating like in the car and see if it will rotate like a constant acceleration for.
Yeah, we could try that. We could try a constant acceleration for a little bit of time. The gravitational acceleration actually is you'd have to have quite a car, a Maserati, okay, and you're probably going to get a ticket doing this. But it'd be an interesting experiment. I'll pay the ticket if you do the. No, I won't. No, I won't. I take no responsibility for you doing this experiment. Yeah, comment, question? They're probably applying a pretty extreme low-pass filter. It's similar to this idea that you construct a model of the thing you're trying to detect, and you ignore information that doesn't match that model. Okay?
And they have also a gyroscope together with the.
I don't think so. Not in not in this version of the iPhone, at least. I don't think there's a gyroscope. There's just an accelerometer. So, yeah. So that's right. So they would apply a low-pass filter so that, for example, they could rule out. I mean, if I'm shaking it back and forth, I can get 1G pretty easily. But I can only get 1G at 2 or 3 hertz. So they could rule out anything that's a higher frequency than a fraction of a hertz. Okay, because on the assumption that you're not really interested in reading your email while rotating the iPhone, right? So, yeah. All right. So this issue of separating tilt from acceleration. By the way, when I did the first version of the lab, the hill climbing experiment, I took one of these iRobots and I mounted the accelerometer on it, and I wrote a little program for this 8-bit microcontroller to climb the hill. And when I ran my first version of the program, the robot started dancing. Literally, it just went like that. And the reason was that the accelerometer was reacting to the robot's motion itself, okay? And it was misinterpreting the acceleration of the robot as a change in tilt, okay? So, this problem of separating tilt from acceleration is difficult. By the way, the accelerometers that you're going to use in the lab basically were invented here at Berkeley in BSAC. They are silicon accelerometers. This is a picture of one of the first versions of the kinds that are absolutely widely used everywhere. All the accelerometers out there in the Nintendo Wii, in airbag systems, in cars, in basically everything out there that uses an accelerometer. The iPhone uses basically this technology invented by Mark Lemkin. And the way that this works is that it has tiny little silicon fingers that are suspended above a substrate and interspersed like that. Actually, I guess one set is suspended, the other set is anchored to the substrate. And what happens when you get a lateral acceleration is these fingers bend, right? When you push the thing this way, the fingers bend this way, and they come closer together on one side, and you can measure a change in capacitance. People had done this before Mark Lemkin came along, but it turned out that it wasn't a very good accelerometer because the fingers would collide, right? They would collide with the substrate. If you put them far enough apart so that they didn't collide, then there wasn't very good sensitivity. So Mark invented a scheme which is a feedback system, which when the fingers come closer together, it applies a countervailing electrostatic force that pushes the fingers away, right? And then all you have to do is measure how much force you have to apply, and that tells you what your acceleration is. So you can keep the fingers perfectly still while this thing is accelerating and measure the acceleration, because you've got this little feedback system that as you're accelerating more, you have to apply more force, So you just measure the amount of force you have to apply. Very clever technique, okay? And that was in his PhD dissertation in 1997. So another way of measuring changes in orientation is using gyroscopes. I talked about that the last time. So here is a picture of a mechanical gyroscope. And this is based on the principle of Newton's first law, which is that things in motion like to stay in motion. And so you've got this spinning wheel. It wants to just keep doing what it's doing, and you have to apply force to get it to change what it's doing. If you mount it on a gimbal, you can rotate the whole object around it without it changing its orientation. Okay? These days, what people use is an optical technique, and the optical technique is just a ring, and it makes the observation that if you're twisting the ring, then the direction that the light travels in one direction around the ring is different than the direction it travels in the other direction. Okay? As you're rotating, okay, you travel less distance to come back to the same point along the direction of rotation, and you can measure that by measuring the optical interference of a coherent light source with a laser. So that's how gyros are done today, and as a consequence, they can be made extremely small. Inertial navigation systems, these are the things that tell an airplane where it is. These use actually a combination of techniques. A lot of people assume that they just use GPS. GPS is not reliable enough for aircraft. Okay? So they have actually rather elaborate systems that use a combination of gyros, accelerometers, and GPS. And they can actually keep pretty accurate track of where they are, even if GPS drops out for several hours. They can still keep pretty accurate track of where they are. But what they do is they use GPS to periodically reset it to a known good point. And then they use the onboard accelerometers and gyroscopes to figure it out from that. Here's a good thought experiment, which is due to Russ Bodick, who some of you may have taken classes from. But one of the problems with iPhones is that the screen is kind of small, right? That's why all of us got suckered into buying iPads, so we would have a bigger screen, right? But one solution to the small screen, if you want to read the New York Times, is you could do something like this, right? You could have a system where you could just sort of move the iPhone over the newspaper like that, right? So what sensors would you use to do that? You think the accelerometer would be a good choice? So I want you to think about this, okay? And the first thing in the next class, we'll discuss what sensors we should use for this problem and what their strengths and weaknesses will be, okay? So think about it, and we'll pick up that thought on Tuesday.